So this is going to be a little bit of a chemistry review, mostly of the early topics, and then we'll try to do a second set of review topics that are for some of the things that we get to a little farther on. This is a beautiful glass bead that was done by Kate Wilkerson, a glass artist in Bisbee, Arizona, and it's beautiful, and it also is a great illustration of the way that different chemical elements, which are incorporated into the glass, interact with light and color in different ways. So I thought that might be a nice first slide. But we're going to start out with some review about particle counts on the next slide. So this is a table that should look familiar to you. It's a table that allows us to look at different chemical species and determine the number of protons, neutrons, and electrons, or the subatomic particle count for that particular version of an element. So let's do the first one together, and then maybe I'll duck in and look at a couple others, and then you can finish filling out this table, or just pause it and make sure that you could finish the rest of the boxes here. The first one is carbon-12, and that carbon-12 is telling us that it's the specific isotope of carbon that has a mass number 12, or carbon-12, and we would write it in the symbol as carbon with a 12 in front of it as a superscript. Now that's the way that we can write what's represented as carbon-12 with a hyphen, but by definition, to be carbon, the atomic number is 6, and therefore it has to have 6 protons. So I'm going to put a 6 in for protons. This carbon has 12 as the sum of protons and neutrons together, so it has to also have 6 neutrons. Now, the mass number is the isotopic number that identifies it. The mass number is what we started out with, writing in front of the C. The mass number of this is 12. If it did have 10 electrons, and that would be unusual for a carbon-12, but if it had 10 electrons, it would actually have a charge of 4 minus, C4 minus, or a negative 4 charge, because 10 electrons is 4 larger than 6 protons. So let's look at the second example. In this case, I'm giving you the proton number 15 and the neutron number 17. That means the mass number for this element must be 32, the sum of protons and neutrons. Now notice that it has a charge of negative 3, and since it has 15 protons but a charge of minus 3, it has to have 18 electrons. So we can fill that in, 18 for the electron number. So what is this element? Well, to figure out what element it is, we simply need to take a look at what is the element that has 15 protons. And that reveals the answer to us, and the isotope is going to be the version of that element that has a mass number of 32. So if you don't have one in front of you, grab a periodic table and find out which element has 15 protons. It's phosphorus, right? Phosphorus is the 15th element, so here I can write 32P, and over here, phosphorus. I'm just going to write POSPH because I can't fit it all in. Phosphorus 32. Now the next one we'll do together for a moment, neon 22. You know that 22 is the mass number and that neon has the abbreviation Ne. And if you look up neon in the periodic table, you'll find it has 10 protons, but to be neon 22, it would have 12 neutrons. The electrons of this neon, well, what's the charge? Over here on the right you can see it doesn't have a charge. The charge is 0. So that means it must have the same number of electrons as protons, 10. The mass number is the sum of protons and neutrons, or the isotope, so it's 22. So I'm going to stop after doing those three, and I'm going to let you do this one, this one, this one, and this one on your own. Remember, the identity of the element will be determined by the number of protons. So you must be given either the number of protons or a way to find it. So for this one, the example that's here, the fourth one, I have a mass number of 58 and a neutron number of 30. That tells me how many protons it must be, and that will tell me the identity. So see if you can finish the rest of this on your own, and we'll go on now to our thinking about electrons. So we've been talking about electron configurations, and the first thing to remember is that the periodic table is actually a big map to help us identify the electron configuration of any element or this address of any electron at a particular position. So energy levels are represented by the rows. So as I go down the periodic table and go to higher and higher energy levels, I'm going further down to rows that are representing energy level 1, 2, 3, 4, 5, 6, and 7. The electron energy levels 1 through 7 each have more and more ways to actually hold electrons, because as we get to higher energy levels, there are more possibilities in the space for how electrons could be held. So we see on level 1, the 1s sublevel is the only kind of orbital that can hold electrons on energy level 1. That's why the first row only has two elements, hydrogen and helium. And as I said, in some ways, you could think of helium as being here because it's a 1s2 position. But from other perspectives, helium really belongs over here on the right because it's a gas, and it's a noble gas like the other noble gases in that last column. So after 1s, we actually find a 2s, a 3s, a 4s, a 5s, all the way down there's an s sublevel. After 2s, we would find the two p's, and you can see in green over here on the right the p block, p1, p2, p3, p4, p5, p6. So we can see that this map is helping us to recognize the filling order of the energy levels and sublevels. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, and then we open up these 4f's that come after the 6s and before most of the 5d. So there's a map to help us practice, and you can come back to that if you want to recognize again how the energy levels and sublevels are laid out on the periodic table. Here's another map like that actually shows numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 through 18 going all the way across for the 18 different columns of the periodic table. But I'm just going to shade in red one of these blocks and see if we can figure out what that block would be. Right here, I'm going to shade in red a block that you can see is in the 4D row. So if I look at that particular position, this is clearly in the 4D block, but it's 4D 1, 2, 3, 4, 5, 6, 7, 8, 9. So that element, if it is neutral, will end with electron configuration 4d9. Of course, the complete electron configuration for that element would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d9. So here's another electron configuration, and in this case you can see the diagonal rule, which is used in some chemistry classes to teach the filling order. But I don't think you need to write out a table like that and use a diagonal rule for the filling order. I really think if you use your periodic table, you can walk up through the blocks and actually find the electron configuration by using the periodic table as a map. What I do like about this is that in fact it shows that on each higher energy level, so from 1 with a 1s to 2 with a 2s and 2p, as I go up in energy level, new sublevels appear with new ways to hold electrons. So in fact there's a 1s, there's a 2s, 2p, there's a 3s, 3p, and 3d, there's a 4s, a 4p, a 4d, and a 4f, and so as I go up in energy level, more electrons can be held in more sublevels with more orbitals. So what I have on the right is actually the electron configuration for the whole periodic table. In other words, this is the filling order, or it's the electron configuration that would be held by an element that would be all the way out to 7p6. And I think if you look on your periodic table, you'll see that 7p6 is not occupied by an element that we normally encounter on Earth. So this is actually the electron configuration that goes all the way from 1s all the way to 7p. So the question is, for any given element, how much of that electron configuration is it using to arrange or configure the electrons that it actually has? So just imagine that I asked you to give the complete correct electron configuration for bismuth. Bismuth has the atomic number 83, so if it's neutral, it would have 83 electrons. Well, if you look, you'll find bismuth down here in the 6p block. And you can see that it's 3 over. So I know this electron configuration is going to end 6p3. And in fact here, I have a table that shows you what electrons bismuth has for each of the rows. So it's walking up 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, and then in the 6th row, 6s2, 4f14, there's the F block that's inserted, and then 5d10, 6p3. So that, written all out, would be the complete electron configuration for the 83rd element, bismuth. This shows what we call the energy level diagram. Instead of just an electron configuration, this kind of diagram actually shows arrows to indicate the electrons at each energy level and sublevel. So what we know is that the Pauli exclusion principle says you can't put more than one electron of a given spin into an orbital, and since there are two kinds of spin, really it's telling us that an orbital like a 1s or one of the 3 2p's, any single orbital can only hold 2 electrons and then it's filled. So sulfur, which is the 16th element, has the electron configuration that you see here, 1s2, 2s2, 2p6, 3s2, 3p4. If I add up those numbers, 2, 2, 6, 2, 4, they will total 16. So when I do an energy level diagram, I'm going to park those electrons, 2 in the 1s, 2 in the 2s, and then 2, 4, 6 in the 2p. Now, that 2p is filled, my 3s is filled, but my 3p needs 4 electrons. So you can see 1, 2, 3, and then the doubling up 4. So that's an energy level diagram that we've practiced as well.